Okay, welcome to chapter 23. This is the amine chapter. So it's a chapter that's a little bit out of place because you've already learned about amines quite a bit, and we've done quite a bit of amine chemistry, but it's such an important functional group and that it ties into a lot of synthetic processes. So we've put it together in one chapter. So some of it is review, some of it is looking at reactions that you've already seen, and then some of it is new or new applications of amines that we kind of skipped over before. This is just an overview of all the sections. I'm going to start with structure, physical properties, and nomenclature. I won't test you on nomenclature, but we should just cover it if it's on its ACS content. Then we're going to do basicity of amines. Now that's important. That's understanding what makes an amine more or less basic. And then preparation of amines. So some of it is review, but actually I think the Gabriel synthesis is new, and reductive amination is a new combo on something that we've already learned. But reducing nitro groups and nitriles and amides, this is all functional groups that we've looked at before. And then we're going to do reactions of amines. So amines and carbonyls, mostly review, right? You've seen how amines react with aldehydes and ketones and carboxylic acids. But there is a little thing that we didn't really cover about amines and Friedel-Crafts, so we'll do that. And then we'll do the reactions of amines with nitrous acid to form diazonium, and those reactions that you can do with those. And then really quickly, the Hofmann elimination. I think you guys saw this in Organic 1. I'm not going to test you on it, but it's another ACS content thing, so we'll quickly look at that. So, amines. Primary amines have one R group and two hydrogens. Secondary, two R groups, so forth. Tertiary amines. And then you can have quaternary amines. They're not called quaternary, they're ammonium salts. So when you have four R groups bonded to nitrogen, then it becomes positively charged and you need a counter ion. And that's why they're called salts. So amines also have a lone pair, right? That's not really drawn in here. It's here in every case, except of course the ammonium salt where you've used it up. And that lone pair really means that there is this hotbed of electron density around the nitrogen. This is where the lone pair resides, right? And that electron density makes the nitrogen a good nucleophile, right? It's electron rich. So you'll see a lot of reactions where you're using that lone pair. Now, can amines be chiral centers? Generally, no, because of that rapid inversion. I don't know if you guys covered this in Organic 1, but basically you can have an sp3 amine, right, with its trigonal planar geometry with the lone pair taking one position, and then you would have, if these substituents are all different, right, you would have a sort of chiral center here. But what happens is that at room temperature, it takes only about 5 kcal per mole to interconvert. So most of the time, amines are going via, inverting via this planar transition state. And as they do that, they lose the stereochemistry that was here. Suddenly, the stereochemistry is flipped, and you're going back and forth. So that stereochemistry does not play into any of the reactions. So we don't consider an amine, even with different functional groups, to be a chiral center. This is not true if you're an ammonium, right? The ammonium is sort of locked into a tetrahedral structure. It is always sp3. And so once it's locked in, then it does retain its chiral center, right? So if all of these were different, then technically, yes, this would be like a chiral center. of course, if you then, do reactions and go back to a neutral amine, then you lose it. So, all right, nomenclature is pretty straightforward. For most of them, you just say the alkyl group and then amine. So if it's ethyl amine, ethyl NH2. If you have to use multiples, say this is triethylamine, so there's 3 ethyl groups, so triethylamine. If you have to say like multiples, you would say maybe N-methyl, N-ethyl. The N just means that ethyl and methyl group are bonded through the nitrogen. Then there's a couple aromatic structures that we should just remember: pyrrole, pyridine, aniline. You'll see those common names on ACS exams. And so here is, this is N-methyl 1-phenyl-propen-2-amine. It's also methamphetamine, it's meth. Why does it have this name, right? So N-methyl is this methyl group, and then the propane comes from here. 1, 2, 3, right? So 1 to the phenyl and 2 to the amine. So that's where this comes from. But it's the alkyl group is still 3, so that's why it's prop. Okay, that's just a quick nomenclature review. Okay, so acid-base chemistry, right? So we're going to learn a lot about amines acting as nucleophiles, but there are also acids and bases. Now, let's start with an amine. This is a neutral amine acting as an acid and giving up a hydrogen, and so then it would become this anionic conjugate base. Now, it really does not want to do this, right? So this is a very weak acid. Here it is, let's see, all the way over here on the scale. It's slightly better than straight alkanes as acids. Alkanes, hate giving up their hydrogens, but it's better, but it's really a horrible acid. So you should really not use this. Right? So you should not use a neutral amine as an acid. That's not the way they react. But they are so this is a protonated amine, and that's actually okay. It's a weak acid, but it's stronger than many organics. Here it is up here. So these here are, the best acids are here, and this is best bases down here, right? So you can see here's carboxylic acid, pretty good acid, and a protonated amine is below that. So it's a better base than, say, just like an alcohol, right? It's a better acid than an alcohol. The OH doesn't really want to go to the O-, but here, because you're going from the NH3+, right, but you're going to a neutral structure, right, you're going to a neutral conjugate base, then that's actually that's a stable conjugate base. So this is an okay acid. And finally, actual neutral amines, right? So neutral amines almost always are bases. How good of a base? Not super great, right? So here are the best bases, and we're all the way up here. So definitely a weak base, but it's stronger than most other neutral organics, right? You'll notice that this is a neutral base, whereas everybody else is charged. Like obviously these are going to be much more basic, but for a neutral compound, it's a pretty great base. And again, when it acts as a base, then you get the cationic conjugate acid, right? So if you see a neutral amine, it's acting as a base, and if you see it protonated, then it's a pretty weak acid, but this also wants to give up that hydrogen and go back to the neutral. Right, so this is a very simplistic view of just a primary amine. Obviously, lots of things will affect the basicity of the base. So let's mostly compare to oxygen, right? So one thing that will make it a better base is being less electronegative, right? Because as a base, you're giving up your lone pair. So the electronegativity of the element will factor into this. And oxygen is more electronegative than nitrogen, right? So say when OH has to give up one of its alone pairs, right, to become positive, it does not like that. It's very electronegative. It did not want to give up its lone pairs, and so it's sad. Nitrogen also would have to give up its lone pair here to become the ammonium. And you know, it's still not super thrilled about this, but it's less electronegative, so we can call that a meh, right? So this would make it a better base, right? Because basically the NH2 is less stable, whereas see the OH, right, is more stable. It wants to hold on to that, to those lone pairs, and so that makes it a weaker base. All right, another big factor is going to be resonance. So again, in this case, you don't want to stabilize that lone pair, right? The lone pair is how it's going to be a good base. So here's NH2 on just an alkyl, and it has no resonance. That lone pair can't That lone pair can't be conjugated elsewhere. It is stuck on the nitrogen, and so it's ready to act as a base, right? That lone pair is available. Let's call it, yeah. So that makes it a better base than, say, aniline. Because now there's quite a bit of resonance, right? I can go here, and then I can move around the benzene ring, right? So I have resonance with the ring. That makes that lone pair less available, and aniline is less basic than a straight alkylamine. Even worse than having resonance with benzene is actually being part of the aromatic ring, right? So this is pearl, and that lone pair is part of that 6pi electron system, right? So this is an aromatic lone pair in a sense. So taking that lone pair away to do base stuff is not what the pearl wants to do, right? It would break its aromaticity. So this is not a good base, right? That lone pair is not available. So you would have to have a really strong acid to deprotonate pyrrole. Okay, the last thing that could affect your basicity is your nearby groups. So here is this is guanidine. Now let's look at the basicity here of this nitrogen and hydrogen group. So if we were going to remove that hydrogen, we would have, sorry, we're not going to remove the hydrogen, we're going to be a base. We're going to pick up a hydrogen and be positive here. Okay, right, so as guanidine acts as a base, it picks up a hydrogen, and now this amine is, this nitrogen, sorry, is positively charged. But there are all of these electron donating groups here, right? These are electron donating groups, and so they're helping out that nitrogen, and they stabilize the cation, right? Specifically on the conjugate acid. Right, so if you're stabilizing the conjugate acid, you're making that original base stronger. And guanidine is actually a pretty strong base because it has two of these electron donating groups. So this nitrogen is pretty basic. So if you're just regular alkylamine again, you don't really have very much donating or withdrawing, so it's sort of in between. But what if you do have an electron withdrawing group, right? This is an amide. Is this more or less basic? So in this case, you have an electron withdrawing group, and then this lone pair is getting sucked into that system, right? It can do resonance with the carbonyl. We've seen plenty of that, right? Where right, so this lone pair, right, is really not available because it's in resonance with the carbonyl, right? The electron withdrawing group is taking up a lot of that lone pair. So lone pair not as available. To be a base. Okay, so amides are actually really weak bases. So here's sort of a quick classification rules. If you're trying to decide who is a stronger base, who's a weaker base, you could start with this. But just to be clear, this does not include substituent effects that we just talked about. It's sort of just basic alkylamines, right? So just to walk you through it, right? So does it have lone pair resonance, right? Is that lone pair being, resonating with another part of the molecule, say an electron withdrawing group or aromatic group, and, is less available? So yes, that would make it a weaker base. And if it's contributing to aromaticity, right, even a weaker base. So pyrrole is weaker than just, say, having a conjugated amine. So this amine, that lone pair, could be conjugated with this double bond. But this is not aromatic, whereas this is. Okay, what if you don't have resonance? Then you're already a stronger base. And then it's asking you to look at the hybridization. Okay, so sp3 tetrahedral, then you're in the strongest of the bases. sp2, right, this is planar. So this, an amide, right? So this is not in resonance with this double bond, right? This here is, but this is not. It's like it's on the same atom as the double bond. So this is not resonance. So this is planar instead of tetrahedral, and this makes it less of a strong base. Now, as I said, this does not include substituent effects at all, right? So here is my amide again with the electron withdrawing group, and it does not have aromaticity, right? It would follow this path here. It would come out as, yes, it has resonance to the carbonyl, but it's not aromaticity, but it's still actually less basic than pyrrole, right? So because of that substituent effect. So those are important effects, and they will jumble the order in a sense. If you have the donating group, it will increase basicity, right? If you have a withdrawing group, it'll decrease it. So here's a quick reminder from the aromatic chapter when we looked at heteroatoms in aromatic structures. So pyridine is aromatic, but the lone pair on the nitrogen is 90 degrees, and it's not actually part of the ring of the conjugated cycle. It's outside of it. So that lone pair is not part of the ring, and it's not in resonance, right? It doesn't I won't say in resonance, but there's no resonance with the ring. So that makes pyridine a weak base. It's okay. I mean, it is a base because that lone pair is available. On the other hand, with pyrrole, that lone pair is part of the aromaticity, right? It is using the lone pair to be aromatic, so it really does not want to lose it. If it did, right, this was a quiz question, right? This is non-aromatic, and that would be its huge loss of energy, right? So pyrrole is a really poor base. And so this is just a quick trend, right? So this way to better bases. So here we have very, very low basicity, right? Same order as an alcohol, right? Amides with the electron withdrawing group, or the pyrroles that are part of the aromatic groups. And then all the way up here, right, we have guanidine again, right? So this is a really strong neutral organic base. So you can see that, like, well, you can't just say, oh, amines are bases. There's a lot of factors that affect basicity. So let's look at a few practice. Rank these from least basic to most basic. Remember, try it at home. I want you guys to try it. Okay, I'm going to do it. So, let's see. We're going to compare all of these nitrogens here. So right away I see this one it is an sp3. It's no resonance, nothing, no electron withdrawing groups or donating groups, right? So this is clearly my most basic, right? That's number 4. Now, right next to it, right, this is sp2. It is basically an aromatic lone pair. So this is my least basic. All right, but now we got to compare pyridine, an okay base, with your pyridine with another nitrogen, right? So now we have something else in the ring. So we are both sp2, and there's both no resonance. But this nitrogen is an electron withdrawing group, right? It is more, nitrogen is more electronegative than just carbon, right? So by inductive effects, basically this benzene ring is, well, this pyridine ring is already less electron rich. So this makes this one less basic. So this is number 2, right? Less basic than this one, which will be number 3. Okay, let's compare in these compounds which nitrogens are more basic. So here we have the lone pair that is aromatic, right? So this is the aromatic lone pair. So that's definitely not probably going to be very basic, right? Whereas this lone pair here, not part of the aromatic structure, it's sp2, but still it's definitely going to be better than the aromatic. So this is the stronger base, well, that nitrogen. Let's say more basic. Okay, now let's compare here. So this is an aniline, well, what's a pyridine with an amine on it. So at first glance, I'm like, oh, this is an amine, sp3, right? Versus this is an sp2. But this amine has resonance, right, with the benzene ring. So actually that lone pair is less available. So that nitrogen is actually more basic, not the NH2. Here's another practice. Here we're saying which will the reaction go forward or backwards, or which way should I draw the arrow? So the trick here is identifying who's going to be the base and who's going to be the acid, and then see which side has the more stable acid and base, right? So here's a neutral amine. That's going to be my base. And on the other side, we're going to make, so this conjugate acid and hydroxy group, right? Now the hydroxy group is a way stronger base than the amine. So what does that mean? It means that maybe I can get a little bit of this to go, but as soon as I form this stronger base, it's going to deprotonate right back, right? It's going to take that hydrogen back and become water. So this is more favorable backwards, right? Opposite directions. Okay, give you a second to do the next two. Ready? All right, so here we have a carboxylic acid. That's a pretty strong acid. And here we've got an amine, so that's a, I don't know, it's an okay, yeah, I mean, it's an okay base. All right, so then let's look on the other side, right? We have a, the conjugate base of the carboxylic acid, right? And this is a really weak base. So this one definitely goes forward, right? So this is a weaker base than the amine, and the carboxylic acid is a stronger acid than this protonated amine. So this goes forward. Now let's look here. We still have carboxylic acid, but now it's paired up with pyrrole, right? And this is a weak base. Let's call it even a really weak base. And so then you would form this, the conjugate, right? And here you would have lost your aromaticity. Right, so this is really unhappy. So actually now this, even though it's a weak base, basically in this reaction, it is now the strongest base. It's certainly more basic than the pyrrole. So this actually goes back this way. The carboxylic acids, they're good acids, but they're not strong enough to deprotonate a pyrrole. So now we're moving on to the preparation of amines. There's a few ways to make an amine, and when we say the synthesis of amines, we're really talking about like changing that R group on the amine, right? Making either a primary or like make a secondary with two R groups, right? How do we install those R groups on our amine? So we're gonna start with ammonia, right? NH3. And like we said, right, this is very basic, right? You have these lone pairs. They're going to act as a nucleophile and do SN2 on, so this is our nucleophile, this is our electrophile. It's just an alkyl halide, right? And it's going to boot off the halide, and we're going to add that R group to our nitrogen. So that will mean it'll go via a ammonium salt, right? This is sort of an intermediate, but there's more ammonia present, right? Which is still a base, and it will deprotonate and give that. So this is deprotonate. And then you form your primary amine. So you have your amine, and it seems like pretty straightforward, except this primary amine is still a nucleophile, right? So what does that mean? That means that it will also come over here and readily attack another alkyl halide. Then you will get two R groups that will get deprotonated either by your primary amine or some more ammonia that you still have in there. And so then you will then get your secondary amine, which I think you're seeing the trend here, still a nucleophile. So it comes down here and it will also attack another alkyl halide. You now have 3 R groups that will be deprotonated. Again, any base is still around. And then you get tertiary amine, but it doesn't stop there. Right, this still a nucleophile, will attack another alkyl halide, and then you will stop at this quaternary ammonium salt. So this is where it actually stops. And that's maybe not what you wanted to make when you set out to make your primary amine at the beginning. So really, this reaction method does not work very well. It's not a good method really for any kind of amine, but especially secondary and tertiary, because even with one equivalence, so you only have one equivalence of your alkyl halide, right, you will still get a mixture, because as soon as you form a little bit of the primary amine, right, you haven't used up all of it yet, and so suddenly this primary amine will start reacting. The reacting rates are similar here, and so you'll end up with a mixture of the primary, secondary, tertiary. They'll all have reacted. The only practical use for this is you could make a primary amine with excess ammonia, right? If you have so much NH3, right, that basically it is always going to be the nucleophile, and then the primary amine doesn't really get the chance to see the electrophile. You need a huge excess of ammonia, but ammonia is cheap, so that can work okay. Also, you could, if you want the ammonium salt, then this is an okay way to do it. Then you just use excess alkyl halide, and you don't care about this chain reaction because that's the chain reaction you want, right? So unless you want a primary amine or an ammonium salt, generally this is not a good method. And you should definitely not use it. Do not use this for trying to do like a synthesis of a secondary or tertiary amine. There's actually a better way of making the primary amine without any competition, and that's called the Gabriel synthesis. Instead of just starting with ammonia, you start with a very specific amine, and that's phthalimide. So remember how we looked at, say, like this section here, like this is like an amide. This would be really not a very good base, right? Because you have that electron withdrawing group. Here you've got, two, let's see, two electron withdrawing groups here, and this is actually makes this amine a pretty good base, a pretty good acid, right? The pK of 10. So it can become deprotonated, to generate your nucleophile, right? And so then once it is deprotonated, you have that lone pair right on the nitrogen. Now this is very basic, and it will be your nucleophile and attack your alkyl halide. So you'll do that first step, right, SN2, and you'll get your alkylated amide. And now you might think, okay, well, like this lone pair is still here, why doesn't it go after a second one, right? But this amide is really not interested. Oops. Because that lone pair is currently busy with a bunch of resonance, right? it can, that lone pair can do resonance on either of these carbonyls, right? So the lone pair is not available. So it's not going to keep reacting. It stops at this intermediate where you just have one R group, and then you do hydrolysis. So it's just basic conditions in water, and you release your amine, which is your product. And what's nice about this is that, this, you just get one primary amine as your clean product, and you just, have a, this is carboxylate, right? You have carboxylate byproduct. It's O minus, right? Because this is basic conditions. But I'm not going to ask you this mechanism. But it's very similar to what we've seen before with the hydrolysis of amides. Okay, so this, though, is still just for primary amines. What if you want to make something else? So you can also prepare amines through reduction reactions, and we've seen this already. So this is basically all review, right? So there's many ways to reduce a nitro group. We've looked at hydrogen over palladium, or iron in acid. Remember the Clemmensen reduction reaction? We said this would be dangerous to use around the NO, not dangerous, but if you used it with the NO2, that its zinc and HCl will also reduce the NO2 to an amine. And also lithium aluminum hydride will also do this. So lots of ways to go from an NO2 to a primary amine. We also saw that nitriles reduced with a strong reducing agent, lithium aluminum hydride, will go to the amine, right? And then you can also reduce amides, again, strong reducing agent. And then you go from the amide to the amine. It's this carbon that is being reduced from the CO double bond all the way to a CH2. And that's actually maybe the main limitation of this. It's great to make all these amines. You can make tertiary and secondary amines, but they will all be CH2 NH or NR2. So the amine might have different substituents, but your carbon next to it will always be CH2 because you're reducing that carbonyl carbon. So maybe that's a downside, and you don't want to do that. So you can also prepare amines from reductive amination of aldehydes and ketones, and this will be able to give you that carbon like R2 and R2 structure, right? So you could get a substituted carbon next to it. In our chapter on aldehydes and ketones, right, we studied how ketones or aldehydes will react with an amine in this reversible way to make an amine. If this is with a primary amine and with a secondary amine, you would get the enamine, right, as your final product. What the reductive amination does is that it combines that first reaction to form the amine with a reduction So you go from the imine to the amine with a weak reducing agent, and we use sodium cyanoborohydride. This is the structure here. It's similar to sodium borohydride, but it's sodium cyanoborohydride. There's a cyano group here, and it's even a weaker source of hydride. And it's nice. It's nice to use this because you'll notice here that this this step, and in this case these are reversible steps, whereas this reduction, this is an irreversible. So to maximize your yield, you want to have this reagent, the sodium cyanoborohydride, in the same pot as your amine and ketone, because then that will help drive the reaction forward. As soon as an amine is formed, the sodium cyanoborohydride is there to take it to the amine, and that drives the reaction forward. Sodium borohydride is a great reducing agent. It would certainly reduce an imine to an amine if you already had this made. But it's so good, right, that it will also reduce the aldehyde and ketone. So you can't have it in the same pot, basically, which is a downside if you're trying to go from these reagents straight to the amine. Then you want to be able to use this milder reducing agent so that you can put everything in the same pot, right? So that's why we use this a different reducing agent for this kind of reaction. What's also nice, this can work sequentially, right? You can start with a primary amine, add one ketone or aldehyde, and so you're adding this moiety here, right? So these get added here, and then you can then purify this and start again, put in a secondary aldehyde or ketone, do the reaction again, and install that group. So you can go, you don't have to make you can make dually substituted amines, and this can work in any order. So that's really useful if you want to make kind of a funky amine with lots of different substituents. You just need to be able to have the right ketone or aldehyde, right, to do that. And also this works intramolecularly. Lots of things do. So if you have at least if you have at least 4 carbons, 1, 2, 3, 4, right, between your amine and your carbonyl, then you can do this, right? So for 6 and 5 membered rings, always preferred, right? So right, so this is how you form this cyclic amine. And here what they're showing, right, is that under these conditions, this amine is just quickly protonated and then reduced. You guys don't have to really, we didn't really show that step necessarily, but in these conditions, it doesn't matter that if this amine is protonated or not. Either this, these are kind of shuffling back and forth, right? Either will reduce to the amine. So this is from Master Organic Chemistry. Thank you for helping me not have to do all of these drawings. But I do like to number mine a little bit differently, right? So this lone pair is attacking here at that carbonyl. So I like to count from here. 1, 2, 3, 4, 5, 6, right? And then this is my ring, right? 1, 2, 3, 4, 5, 6. And then this was off of 6, so I put that there. But I think that helps. I mean, that's how I like to count my rings. And then I know immediately what size ring to draw from the get-go. Just keep in mind that the nitrogen is now incorporated in the ring, okay? It's not an NH2 like bonded to a ring, it's in the ring. All right, here's some practice problems. I'm gonna do one with you guys and then maybe just write these in the notes for later. So let's see. So it says draw the product of each reactions. These are all reductive aminations. I'm gonna show the intermediate, but you don't have to. So this is an aldehyde. So there's a hydrogen here. And what is my amine? NH2 and then a CH3. So I definitely have CH3 here. And so this would be on my amine intermediate, and then with the reductive amination, that's the product. So I'm gonna let you guys do the rest, but I'll have these in the slides later. Same thing with this one. This is sort of a retro. What amines and carbonyls are required to form the following structures, right, via reductive amination. And so there's different ways you could chop this up in a sense, right? You can chop this up here, or you can chop this up here. And as you chop, right, keep going down till you get to a primary amine. I'll post this one in the slides as well. Okay, this one is pretty fun. This is dopamine, right? And you can pretty easily make it from the hydrolysis of this acetal in compound X. So this exercise is to have you find all the different ways of installing this amine, right? There are 6 possibilities. So here's one, right? If I take, if I take an alkyl halide, then I can do this with NH3 in excess. Definitely lots of excess, right? This is an alkyl halide, but if I have NH3 in excess, then I can turn this into this amine. So this is how this exercise goes, right? Find 5 other reagents and the conditions to make the amines. And bonus, then try to make all your reagents that you came up with, try to make them from this structure. Obviously, you're going to have to use reactions from the the benzene chapter from aromatic reactions, you're going to have to use some carbonyl chemistry, right? So this was starting to pull in all of the different reactions that you guys know. So I'll post these answers on the slides as well.